Correction for this chapter. In mathematical formulae, instead of I, hear 1.
Relativity, the Special and General Theory, by Albert Einstein. Continuing Part 2, the General Theory of Relativity, Sections 24 through 26. Section 24. Euclidean and non-Euclidean continuum. The surface of a marble table is spread out in front of me. I can get from any one point on this table to any other point by passing continuously from one point to a neighboring one and repeating this process a large number of times, or, in other words, by going from point to point without executing jumps. I am sure the reader will appreciate with sufficient clearness what I mean here by neighboring and by jumps, if he is not too pedantic. We express this property of the surface by describing the latter as a continuum. Let us now imagine that a large number of little rods of equal length have been made, their lengths being small compared with the dimensions of the marble slab. When I say they are of equal length, I mean that one can be laid on any other one without the ends overlapping. We next lay 4 of these little rods on the marble slab so that they constitute a quadrilateral figure, a square, the diagonals of which are equally long. To ensure the equality of the diagonals, we make use of a little testing rod. To this square we add similar ones, each of which has 1 rod in common with the first. We proceed in like manner with each of these squares until finally the whole marble slab is laid out with squares. The arrangement is such that each side of a square belongs to 2 squares and each corner to 4 squares. It is a veritable wonder that we can carry out this business without getting into the greatest difficulties. We only need to think of the following. If, at any moment, 3 squares meet at a corner, then 2 sides of the 4th square are already laid, and as a consequence, the arrangement of the remaining 2 sides of the square is already completely determined. But I am now no longer able to adjust the quadrilateral so that its diagonals may be equal. If they are equal of their own accord, then this is an especial favor of the marble slab and of the little rods about which I can only be thankfully surprised. We must needs experience many such surprises if the construction is to be successful. If everything has really gone smoothly, then I say that the points of the marble slab constitute a Euclidean continuum with respect to the little rod, which has been used as a distance, line interval. By choosing one corner of a square as origin, I can characterize every other corner of a square, with reference to this origin, by means of 2 numbers. I only need state how many rods I must pass over when, starting from the origin, I proceed towards the right and then upwards in order to arrive at the corner of the square under consideration. These 2 numbers are then the Cartesian coordinates of this corner with reference to the Cartesian coordinate system, which is determined by the arrangement of little rods. By making use of the following modification of this abstract experiment, we recognize that there must also be cases in which the experiment would be unsuccessful. We shall suppose that the rods expand by an amount proportional to the increase of temperature. We heat the central part of the marble slab, but not the periphery, in which case 2 of our little rods can still be brought into coincidence at every position on the table. But our construction of squares must necessarily come into disorder during the heating, because the little rods on the central region of the table expand, whereas those on the outer part do not. With reference to our little rods, defined as unit lengths, the marble slab is no longer a Euclidean continuum, and we are also no longer in the position of defining Cartesian coordinates directly with their aid, since the above construction can no longer be carried out. But since there are other things which are not influenced in a similar manner to the little rods, or perhaps not at all, by the temperature of the table, it is possible, quite naturally, to maintain the point of view that the marble slab is a Euclidean continuum. This can be done in a satisfactory manner by making a more subtle stipulation about the measurement or the comparison of lengths. But if rods of every kind, i.e., of every material, were to behave in the same way as regards the influence of temperature when they are on the variably heated marble slab, and if we had no other means of detecting the effect of temperature than the geometrical behavior of our rods in experiments analogous to the one described above, then our best plan would be to assign the distance 1 to 2 points on the slab, provided that the ends of one of our rods could be made to coincide with these 2 points. For how else should we define the distance without our proceeding being in the highest measure grossly arbitrary? The method of Cartesian coordinates must then be discarded and replaced by another which does not assume the validity of Euclidean geometry for rigid bodies. Footnote. Mathematicians have been confronted with our problem in the following form. If we are given a surface, e.g. an ellipsoid, in Euclidean three-dimensional space, then there exists for this surface a two-dimensional geometry, just as much as for a plane surface. Gauss undertook the task of treating this two-dimensional geometry from first principles without making use of the fact that the surface belongs to a Euclidean continuum of 3 dimensions. If we imagine constructions to be made with rigid rods in the surface, similar to that above with the marble slab, we should find that different laws hold for these from those resulting on the basis of Euclidean plane geometry. The surface is not a Euclidean continuum with respect to the rods, and we cannot define Cartesian coordinates in the surface. Gauss indicated the principles according to which we can treat the geometrical relationships in the surface, and thus pointed out the way to the method of Riemann of treating multidimensional, non-Euclidean continua. Thus it is that mathematicians long ago solved the formal problems to which we are led by the general postulate of relativity. End footnote. The reader will notice that the situation depicted here corresponds to the one brought about by the general postulate of relativity. Section 23. End of section 24. Section 25. Gaussian coordinates. According to Gauss, this combined analytical and geometrical mode of handling the problem can be arrived at in the following way. We imagine a system of arbitrary curves, see Figure 4, drawn on the surface of the table. These we designate as U-curves, and we indicate each of them by means of a number. The curves u equals 1, u equals 2, and u equals 3 are drawn in the diagram. Between the curves u equals 1 and u equals 2, we must imagine an infinitely large number to be drawn, all of which correspond to the real numbers lying between 1 and 2. We have then a system of U-curves, and this infinitely dense system covers the whole surface of the table. These U-curves must not intersect each other, and through each point of the surface one and only one curve must pass. Thus a perfectly definite value of u belongs to every point on the surface of the marble slab. In like manner, we imagine a system of V-curves drawn on the surface. These satisfy the same conditions as the U-curves. They are provided with numbers in a corresponding manner, and they may likewise be of arbitrary shape. It follows that a value of u and a value of v belong to every point on the surface of the table. We call these two numbers the coordinates of the surface of the table, Gaussian coordinates. For example, the point P in the diagram has the Gaussian coordinates u equals 3, v equals 1. Two neighboring points, P and P prime on the surface, then correspond to the coordinates P colon u, v, P prime colon u plus du, v plus dv, where du and dv signify very small numbers. In a similar manner, we may indicate the distance, line interval, between P and P prime, as measured with a little rod, by means of the very small number ds. Then, according to Gauss, we have ds squared equals g sub 1, 1 du squared plus 2g sub 1, 2 du dv plus g sub 2, 2 dv squared, where g sub 1, 1, g sub 1, 2, g sub 2, 2 are magnitudes which depend in a perfectly definite way on u and v. The magnitudes g sub 1, 1, g sub 1, 2, and g sub 2, 2 determine the behavior of the rods relative to the u-curves and v-curves, and thus also relative to the surface of the table. For the case in which the points of the surface considered form a Euclidean continuum with reference to the measuring rods, but only in this case, it is possible to draw the u-curves and v-curves and to attach numbers to them in such a manner that we simply have ds squared equals du squared plus dv squared. Under these conditions, the u-curves and v-curves are straight lines in the sense of Euclidean geometry, and they are perpendicular to each other. Here the Gaussian coordinates are simply Cartesian ones. It is clear that Gauss coordinates are nothing more than an association of two sets of numbers with the points of the surface considered, of such a nature that numerical values, differing slightly from each other, are associated with neighboring points in space. So far, these considerations hold for a continuum of 2 dimensions. But the Gaussian method can be applied also to a continuum of 3, 4, or more dimensions. If, for instance, a continuum of 4 dimensions be supposed available, we may represent it in the following way. With every point of the continuum, we associate arbitrarily 4 numbers x sub 1, x sub 2, x sub 3, x sub 4, which are known as coordinates. Adjacent points correspond to adjacent values of the coordinates. If a distance ds is associated with the adjacent points P and P', this distance being measurable and well defined from a physical point of view, then the following formula holds. ds squared equals g sub 1 1 dx sub 1 squared plus 2g sub 1 2 dx sub 1 dx sub 2 ... plus g sub 4 4 dx sub 4 squared, where the magnitudes g sub 1 1, etc., have values which vary with the position in the continuum. Only when the continuum is a Euclidean one is it possible to associate the coordinates x sub 1 to x sub 4 with the points of the continuum, so that we have simply ds squared equals dx sub 1 squared plus dx sub 2 squared plus dx sub 3 squared plus dx sub 4 squared. In this case, relations hold in the 4-dimensional continuum which are analogous to those holding in our 3-dimensional measurements. However, the Gauss treatment for ds squared which we have given above is not always possible. It is only possible when sufficiently small regions of the continuum under consideration may be regarded as Euclidean continua. For example, this obviously holds in the case of the marble slab of the table and local variation of the temperature. The temperature is practically constant for a small part of the slab, and thus the geometrical behavior of the rods is almost as it ought to be according to the rules of Euclidean geometry. Hence the imperfections of the construction of squares in the previous section do not show themselves clearly until this construction is extended over a considerable portion of the surface of the table. We can sum this up as follows. Gauss invented a method for the mathematical treatment of continua in general, in which size relations, distances between neighboring points, are defined. To every point of a continuum are assigned as many numbers, Gaussian coordinates, as the continuum has dimensions. This is done in such a way that only one meaning can be attached to the assignment, and that numbers, Gaussian coordinates, which differ by an indefinitely small amount, are assigned to adjacent points. The Gaussian coordinate system is a logical generalization of the Cartesian coordinate system. It is also applicable to non-Euclidean continua, but only when, with respect to the defined size or distance, small parts of the continuum under consideration behave more nearly like a Euclidean system, the smaller the part of the continuum under our notice. End of section 25. Section 26. The space-time continuum of the special theory of relativity considered as a Euclidean continuum. We are now in a position to formulate more exactly the idea of Minkowski, which was only vaguely indicated in section 17. In accordance with the special theory of relativity, certain coordinate systems are given preference for the description of the 4-dimensional space-time continuum. We called these Galilean coordinate systems. For these systems, the 4 coordinates x, y, z, t, which determine an event, or in other words, a point of the 4-dimensional continuum, are defined physically in a simple manner, as set forth in detail in the first part of this book. For the transition from one Galilean system to another, which is moving uniformly with reference to the first, the equations of the Lorentz transformation are valid. These last form the basis for the derivation of deductions from the special theory of relativity, and in themselves they are nothing more than the expression of the universal validity of the law of transmission of light for all Galilean systems of reference. Minkowski found that the Lorentz transformations satisfy the following simple conditions. Let us consider two neighboring events, the relative position of which in the four-dimensional continuum is given with respect to a Galilean reference body K by the space coordinate differences dx, dy, dz, and the time difference dt. With reference to a second Galilean system, we shall suppose that the corresponding differences for these two events are dx prime, dy prime, dz prime, dt prime. Then these magnitudes always fulfill the condition footnote. Cf. Appendices 1 and 2. The relations which are derived there for the coordinates themselves are valid also for coordinate differences, and thus also for coordinate differentials, indefinitely small differences. End footnote. Dx squared plus dy squared plus dz squared minus c squared dt squared equals dx prime squared plus dy prime squared plus dz prime squared minus c squared dt prime squared. The validity of the Lorentz transformation follows from this condition. We can express this as follows. The magnitude ds squared equals dx squared plus dy squared plus dz squared minus c squared dt squared, which belongs to two adjacent points of the four-dimensional spacetime continuum, has the same value for all selected Galilean reference bodies. If we replace x, y, z, square root of quantity minus 1 and quantity ct by x sub 1, x sub 2, x sub 3, x sub 4, we also obtain the result that ds squared equals dx sub 1 squared plus dx sub 2 squared plus dx sub 3 squared plus dx sub 4 squared is independent of the choice of the body of reference. We call the magnitude ds the distance apart of the two events or four-dimensional points. Thus, if we choose as time variable the imaginary variable square root quantity minus 1 and quantity ct, instead of the real quantity t, we can regard the spacetime continuum, in accordance with the special theory of relativity, as a Euclidean four-dimensional continuum, a result which follows from the considerations of the preceding section. End of section 26.